Assalamualaikum and hello everyone. We are from group 10, are going to be presenting about prostate cancer dataset for our STA602 group project. So this is the group members for our project. The first one we have me, Amira Natasha binti AZLI. Next is ISMAIL FAHMI bin Jaafar, and the last one is ALIYA Natasha binti ZAKARIA.
My name is ALIYA Natasha binti ZAKARIA, so I will start with the project objective. The first one is to identify the most significant predictors of cancer volume among the independent variables, such as PSA level, weight, age, benign prostatic hyperplasia, seminal vesicle invasion, capsular penetration, and Gleason score. Second objective is to determine the regression model for dummy variables such as Gleason score and seminal vesicle invasion. Third is to identify the presence of outlier and influential cases in this dataset. Our data description. First of all, we are using secondary data since our lecturer provided it. This dataset contains a record of 97 men who were about to undergo radical prostatectomies. The variable mainly concerned with is the cancer volume as the dependent variable. It also focuses on additional variables that may influence the cancer volume. Those independent variables include PSA level, weight, age of the patient, benign prostatic hyperplasia, seminal vesicle invasion, capsular penetration, and Gleason score. In this dataset, we have about two dummy variables, which are the Gleason score, which is the sum score whether it is 6, 7, 8, and seminal vesicle invasion with 1 referring to the presence of the seminal vesicle and 0 referring to absence. Next, I will discuss our special topic, which are dummy variable. Our first dummy variable is seminal vesicle invasion, X5. However, it has already converted this variable into a binary variable with the values 1 for presence and 0 for absence. For the second dummy, our variable is the Gleason score. In this dataset, it used a grade disease using the total score of two patterns, and the sum score must be either 6, 7, or 8. So we use the information in the table and reformat it to the qualitative variable, which is low to 6 is equal to 6, 7 is equal to intermediate, and 8 to height is equal to height. For the Gleason score, we divided it into two dummy variables for low X7 and intermediate X8 and high as a benchmark in this dataset. This is the estimated equation for the dummy variable. For the first one, seminal vesicle invasion, we are going to substitute 1 into X5 from the overall estimated regression function for the present equation and substitute 0 into X5 for the absence equation. Second is for the variable Gleason score. We substitute 1 into X7 for the low equation, 1 into X8 for the intermediate equation, and 0 into X7 and X8 for the high equation. So the next part I'm going to explain is the significance of the study. From this project, regression analysis somehow help us to understand how different factors can influence an outcome. This means how our listed independent variable can impact the cancer volume. Second, it also helps us to identify which factors play a major role in disease progression and severity. It also helps us spot outliers in the data and choose the most important predictor. In addition, this approach improves our understanding of prostate cancer and how it develops. Now, we are going to explain the result that we get from the multiple linear regression analysis. So, this is the result of our parameter estimates. Looking at the parameter estimates column, we can design our regression equation using the numbers provided. We use the variables table to generate the equation. We get the equation as y hat equal to 8.71888 minus 0.02251 x1 minus 0.16643 x2 plus 0.80287 x3 plus 0.04798 x4 plus 1.94100 x5 plus 0.00185 x6 minus 3.9469 x7 and 4.45495 xa. Next is our relevant statistical output. For the first one is R squared and adjusted R squared. From the value in the table, we can see that our R-square is 0.6129, and that means 61.29% total variation in cancer volume that can be explained by age, benign prostatic hyperplasia, capsular penetration, PSA level, seminal vesicle invasion, weight, low and intermediate. For the adjusted R-square, our value is 0.5777, and that means 57.77% total variation in cancer volume that can be explained by all independent variables. Meanwhile, another 42.23% can be explained by other factors that are not included in the model. Next, we will examine the p-value obtained from the result. We can already draw conclusion based on the values. We compare the p-value with an alpha of 0.05. As we can see, only 4 variables are relevant in this model, which is capsular penetration, PSA level, low and intermediate, because the p-value is less than 0.05. The remaining 5 include intercepts that are not significant in this model is intercept, age, benign prostatic hyperplasia, seminal vesicle invasions, and weight. This analysis includes both dummy variables. The following lesson is about ANOVA, which is used to determine the significance of a model. We will compare the p-value with an alpha of 0.05. So first, we test the hypothesis that our H0 is beta 1 equal to beta 2 equal to beta 3 equal to beta 4 equal to beta 5 equal to beta 6 equal to beta 7 equal to beta 8 and equal to 0. And our H alternative is that not all beta i's are 0. We reject H null since our p-value is less than 0.001, which is less than alpha of 0.05. This suggests that our model is significant.
The next part is model adequacy checking. The first one is residual analysis. The linearity and homoscedasticity checking, both of them have the same scatter plot, which is residual versus fitted value. Residual versus fitted value plot shows possible violation of linearity assumption. There's a potential of non-linear relationship. And for homoscedasticity checking, the plot shows the spread of high fitted values, so it suggests there is no constant variance. The normality using histogram for residual shows that the histogram suggests a right-skewed distribution, which means that residual are not normally distributed. And for independence checking, we are using Durbin-Watson test. It shows that Durbin-Watson D equal to 2.131. The value is close to the ideal value of 2, that indicates that a little to no autocorrelation in the residuals. The next part of model adequacy checking is checking for multicollinearity. Based on the table of variance inflation, VIF, and tolerance, it shows that all VIF values are below 10. So, the multicollinearity does not a major issues in this model. The next part is divided into 2 categories. The first one is outlier detection and influential cases detection. There are 2 things in the outlier detection. The first one is standardized residual that contains a standard error of residual versus predicted value of cancer volume. While the second one is studentized residual that shows the observation 55, 91 and 94 are the outlier because the value exceeds 3, even that there are 97 observations, so our n is greater than 30. And the cutoff point for value standardized residual is greater than 3. For our influential cases detection, we are using Cook's distance, leverage, DF fits, and DF beta. These are the list of cutoff point for each influential cases given that n is 97 and parameter p is equal to 9. This is treatment for outlier and influential outlier. The first is identification of outlier and influential observation. Using the previous analysis, the regression model can be improved by identifying the outlier and influential data points using the diagnostic that I mentioned before. The second step, we can exclude the observation that exceed the cutoff points of Cook's distance. A new dataset that was created with a new name, Prostate Cancer _clean. Using the new dataset to rerun the regression analysis for the regression model and to find the parameter estimates and model adequacy. Last but not least, doing the data transformation. We have an option to do the data transformation. Further explanation in the next slide.
My name is Amira Natasha binti AZLI, and I am going to be presenting about transformation to correct model inadequacies. Data transformations play a crucial role in addressing model shortcomings like skewness, non-normality, non-linearity, and heteroskedasticity, ensuring adherence to essential assumptions such as normality and homoskedasticity. The first one, we have normality assumption. The null hypothesis is the prostate cancer data follows a normal distribution, and the alternative hypothesis is the prostate cancer data does not follow normal distribution. Based on the table above, since the p-value is 0.150, which is greater than the significance level of 0.05, we fail to reject the null hypothesis. The error terms are normally distributed, therefore the log transformation is significant to use. The histograms illustrate the effect of applying a log transformation to correct model inadequacies related to normality. Before transformation, the residual graph show a skewed distribution with a heavy tail, indicating a violation of the normality assumption in regression analysis. This suggests that the original model may not provide reliable inferences. After applying the log transformation, the graph demonstrates a more symmetric and bell-shaped distribution of residuals, aligning more closely with a normal distribution. This improvement suggests that the transformation effectively stabilized variance and reduced skewness, enhancing the model's reliability and accuracy in making predictions. Next, the QQ plots illustrate the impact of log transformation on the normality of residuals. Before transformation, the residual plot deviates significantly from the diagonal line, particularly at the tails, indicating that the data does not follow a normal distribution. This deviation suggests that the model's assumption of normality are violated, which can affect the accuracy of statistical inferences. After applying the log transformation, the plot shows residuals that align more closely with the diagonal line, indicating a more normal distribution. This improvement suggests that the transformation successfully corrected the skewness and made the residual more normally distributed, enhancing the model's validity. Next, we move to linearity and constant variance assumption. The residual plots illustrate the impact of log transformation on linearity and constant variance, homoskedasticity. Before transformation, the residual plot exhibits a clear funnel shape where variability increases as predicted value increase. This pattern suggests heteroskedasticity, meaning that the model's assumption of constant variance is violated, which can lead to inefficient and biased parameter estimates. After applying the log transformation, the plot shows a more evenly scattered distribution of residuals around the horizontal line, indicating that variance is now more constant across different levels of predicted values. This suggests that the transformation successfully stabilized variance and improved the model's linearity, leading to more reliable regression results. Last but not least, conclusion. In this project, several independent variables were examined to ascertain their importance in forecasting cancer volume. This study intends to improve the understanding and treatment of prostate cancer by identifying these important indicators and assisting in the creation of more efficient regression models. Our findings demonstrated that certain variables had a strong and significant relationship with cancer volume, whilst others had no significant influence. Our research found that capsular penetration, PSA level, and Gleason score were the most significant predictors of cancer volume, with p-values less than 0.05. In addition, we formed a regression model with dummy variables to adjust for categorical predictors including Gleason score and seminal vesicle invasion. The inclusion of these variables resulted in a better representation of their effect on cancer volume. Moreover, observation 55, 91, and 94 were classified as outliers due to their significant deviations, whereas observation 32, 47, 96, and 97 had a high leverage, indicating potential influence on the regression model. The implication of this study extend to both medical research and clinical practice. Healthcare providers can more accurately determine the severity of prostate cancer and make well-informed decisions about patient care by identifying important predictors. Additionally, the regression model offers a quantitative method for calculating the amount of cancer, which may help with treatment planning and early identification. There are some drawbacks and limitations despite the contributions. The result of this study may not be as broadly applicable as they could be due to the small sample size of 97 patients. Furthermore, the dataset only contains a small number of variables, therefore, other possible factors that could affect the volume of cancer were not taken into account. In conclusion, the findings would be more solid in further research if the dataset were expanded to include more patients. Prostate cancer progression may be better understood by taking into consideration extra elements such as genetics, lifestyle choices, and environmental exposures. That is all from us. Thank you.